All right, so this is lab 3, circuits. The purpose of this lab is to understand circuit analysis, specifically the relationship between voltage and current when resistors and capacitors are present, and we want to practice using ammeters and voltmeters to measure quantities of current and voltage. Current and voltage found were, so the results were that the current and voltage found were similar to the theoretical values, and the total change and potential difference should sum to zero in a circuit, and the times to charge and discharge the capacitor were almost the same as the predicted values. So some key concepts for the first experiment, we have to know Kirchhoff's loop rule, the junction rule, and just a preview for the second experiment, resistor and capacitor. So Kirchhoff's loop rule basically just says that the sum of the potential difference as you traverse through a circuit should equal zero. The junction rule says that the current going into a node should equal the current going out of the node. And here are the equations for resistor and capacitor in a circuit. All right, so for the first experiment, we have two batteries and both of 1.5 volts, which add up to 3 volts. And we have a 47 ohm resistor and a 100 ohm resistor. You can see the setup on the right. And we expected the value of the current to be 0.02 amps. And this was found by taking the voltage and dividing it by the total resistance. But the actual value was just slightly higher at 0.0285 amps. So some possible sources of error for that could have been an inaccurate reading of the ammeter or rounding errors. And on the left over here, you can see the basically each point in this circuit, and we model a graph showing the voltage. So at the start, point A to point B, we should gain 3 volts. And then as we go through each of these points, you should notice a significant drop in voltage. And this is due to the fact that that there are resistors here. So the first drop was measured to be 0.72 volts, second negative 2.3. And when you calculate the resistance, the actual values are, or the recorded values are a little bit significantly different from the actual, like what the predicted value should be. This just could have been an accurate reading of the current or the voltage drop. So for the second part of the experiment, we have a capacitor, and we use this capacitor to charge light bulbs. I wasn't able to get the video up, but this is a picture showing the setup, and what we need to know for this is the amount of time it takes for a capacitor to charge and discharge, since the equation is exponential, which means that we should predict the time it takes to decay that it should decay exponentially. So for the first bulb, we used a 3.7 ohm resistor, and we found that charged at about 14 seconds and discharged at about 17 seconds. This was pretty close to the predicted value, which we can see over here, and that is at 18.5 seconds. When we do the same for the second bulb, we see that it's pretty close to the predicted value again. So any errors could have been misreading the timer or just having an incorrect capacitance value. So the times taken to discharge both bulbs are slightly similar to the predicted model, and that supports the equation for discharging a capacitor. So what if we charge the capacitor with no resistor in the circuit? And how quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? And the answer is that ideally it should charge instantaneously, but because resistance is zero, that must mean the current would reach the capacitor at 0 seconds. And the capacitor would reach the same potential difference as the battery instantaneously. But in reality, although the data was not collected, it can be concluded that the capacitor would not charge instantly. That is because all materials have some amount of resistance, including the wires connecting the capacitor to the battery.